Okay, so here I'm going to go over the FRQs for the Unit 7 Unit 7 progress check. So here we have the very first one. We're dealing with a pendulum that is made from an object mass m. It's in the shape of a triangle of height h, and it is hung vertically from this pivot point, and it can be modeled. So the mass of the object is uniformly distributed across the area of the triangle, and it can be modeled as a linear mass density, where c is a positive constant and y is the distance from the pivot to the locations on the object. So first we have to derive an expression for the period of the object when it's undergoing small oscillations about the pivot point, and express it in terms of hm and physical constants as appropriate. All right, so to approach this problem, there's an equation that we're going to be learning about for the last lesson. This is the period of a physical pendulum, and it's equal to 2 pi times the square root of I over mg times d, where I is the moment of inertia, and d is the distance of the center of mass from the axis of rotation. Okay, so in order to come up with this expression, we need to figure out the moment of inertia. We have to have an expression for moment of inertia, and we have to come up with an expression for the distance of the center of mass. Well, the equation for moment of inertia is the integral of r squared dm. And in terms of what our dm is going to be, well, if you remember from when we were doing center of mass and dealing with objects with a non-uniform mass distribution, well, we know that the linear mass density is in units of kilograms per meter, right? So the total mass of the object, right, is going to be, if you have a linear mass density, then you just take the linear mass density times the length of the object, and that gives you the total mass. And if it's just a general function, you have this expression over here. So the dm is just the linear mass density times dy, right, or dx or dl, whatever it is, whatever symbol you want to use for the characteristic length of the object. So here, using the variables that they give us, our r, right, was the distance that we're going to be integrating, right? So we're going to be using the variable y, okay, as the, as we look at how the moment of inertia or how the mass changes as we go away from the pivot point. So that's basically, instead of r, we're going to be using y. And in terms of our bounds of integration, we're going to be integrating from the pivot point y equals 0 till the end of the triangle where y equals h. So let's just plug in our values. Here we're going to integrate from 0 to h y squared, okay, times dm, which we're going to write dm as the linear mass density times dy. So this is our equation for the linear mass density. So just some constant times y. So c times y times dy. All right. And what we can do, we can simplify this. So I'm just going to move out the constant c. And then I know that y squared times y is y cubed dy. And then the integral of y cubed is 1/4 y to the 4th. All right, so we have c times 1/4 y to the 4th power. Okay, and we're going to evaluate that from 0 to h. And then we end up with an expression ch to the 4th power divided by 4. All right, so that's our moment of inertia. That's our expression for a moment of inertia. And now we need an expression for the distance of the center of mass from the axis of rotation. So for that, what we need to do is we got to use the equation for the center of mass. So the center of mass equation, it's on the equation sheet. It's going to be 1 over m times the integral of r dm. All right, and we already have an expression for dm. That's just c times y, right? So it's c dm is c y dy. And now our r is going to be just y. So I'm going to write 1 over m times the integral from 0 to h of y times cy dy. And similar process to what we just did before, very similar. So I'm going to just factor out the c, it's just a constant. And then I'm going to evaluate, actually I won't skip any steps. So from 0 to h for y squared dy, right? Because y times y is y squared. And then the integral of y squared is 1/3 y to the third power. All right, so we got c over m times 1/3 y to the third power, evaluated from 0 to h. Okay, so that's just going to be ch cubed over 3m. All right, and that's our expression for d. And now we get to plug it into the equation for the physical pendulum. So we got 1 over 2 pi times the square root of I, which I is going to be ch to the fourth power divided by 4. And then we're going to divide that by mg times d, which is ch to the third power divided by 3m. And it's a nasty expression, and there's quite a bit of canceling to do. So let's start canceling out some terms. We have a c in the denominator here and a c up here. That cancels out. We have an h cubed over here. That's going to cancel out with the h to the fourth power, right? So we just have a single h in the numerator. One of the m's cancels out. And let's clean up this mess. So we have here 1 over 2 pi times the square root of h over 4 divided by g over 3. All right, want to make sure we don't mess this up. All right, so then let's simplify this expression even further. And we have 1 over 2 pi times the square root of 3h over 4g. So 3/4 h over g, or the square root of 3/4 h over d times 2 pi. So that's our period of our physical pendulum, our little triangle pendulum here. And then that's part I. So now we have another scenario. We have here a triangle that's twice as big as the original triangle, but it has the same mass. So the second object has the same mass, m, as the first object's uniformly distributed. Pivot point is located at distance d above the second object's center of mass, where d is the distance between the original object's center of mass and pivot point. So it seems a bit convoluted, but if anything, they're making it easy for you, because you'll see we have to indicate whether the oscillation period of the second object is longer than, shorter than, or the same as the period of the original object. Justify your answer. Well, if we look at our equation here, right, we know that the m's are the same. G is just gravity, that's going to stay the same. And the distance d, right, the distance d of the center of mass from the axis of rotation, that's also the same. So the only difference in the two scenarios is the moment of inertia, right? So we know that the moment of inertia for the second object, it has to be greater than the first object. The reason for that, it has to do with the mass distribution. So for the moment of inertia equation, we always know it's proportional to m times r squared, right? So whether or not it's a ring or a point mass, that's mr squared, or it's a solid disk, 1/2 mr squared, or it's a solid sphere, which is 2/5 mr squared. Doesn't matter in terms of like what the equation is. What matters is that the mass distribution, right, for the larger triangle is distributed further away from the axis of rotation. So the second moment of inertia, actually, I'll just mention it now because for part B, we have to know it. It's technically 4 times as large as the moment of inertia of the first object. And if you think about it, it makes sense, because like just imagine a more simple scenario. Say you have 2 disks, right? And then both disks have the same mass, but the second disk is twice the radius of the first disk. Well, because the moment of inertia of a disk, 1/2 mr squared, if you have twice the radius, that quantity is squared, so it ends up having 4 times the moment of inertia. And it's the same argument here with the triangle, is that at least the moment of inertia about the center has to be 4 times as large, and we're going to see that in a second. So this I I'm writing down is the moment of inertia about the center. But either way, it's definitely larger. So to answer part 2, okay, justification. So we know that the period is definitely longer than the period of the original object. And the reason why is because the moment of inertia of the second object has to be larger than that of the first object, and then everything else stays the same, right? Same mass, same distance from the axis of rotation, with that center of mass that is. Everything else in the equation stays the same. Only the moment of inertia gets bigger. Therefore, the period has to be larger. And then finally, for part B, we have to figure out an expression for the moment of inertia of the second pendulum. So IP2 is the moment of inertia of the second pendulum in terms of D, IP1, M, and physical constants as appropriate. So in order to figure this out, right, we're going to need to use this fact, right, that the moment of inertia of the second object about its center is 4 times that of the first object, right? So geometrically, the triangle is twice as large, so the moment of inertia has to be 4 times as much. But the thing is, this object's not rotating about its center. It's rotating about this pivot point. So we're going to need to use the parallel axis theorem, right? So the center of mass of the object is some distance d away from the pivot point. So remember that in that situation, you have to use parallel axis theorem. All right, and basically you just got to add an md squared term. So let's write an equation for the physical pendulum, the first physical pendulum, IP1. Well, that equals the moment of inertia about its center plus this md squared term. And they both have the same mass, so it's the same m, same d, same everything. The only difference is that they have a different moment of inertia about the center. So this is for the physical pendulum 2 plus md squared. And we're going to have to do a substitution, right? So we have to write IP2 in terms of IP1. So I know that, let's see here. So I know that I2, so the moment of inertia of the larger triangle about its center is going to be 4 times larger. So what I'm going to do is I'm going to write an expression for I1. I'm going to perform a substitution. That's IP1 minus md squared. And then I'll substitute that in. I know that I2 is 4 times I1. So now I'm going to substitute that into here. So IP2 is equal to I2, which is 4I1, and I1 is this. So 4 times IP1 minus md squared. All right, and then plus md squared. And then when you work out the math, you get 4 times the moment of inertia of the physical pendulum plus 3md squared. And that's our answer. All right. So this problem was, not trivial, just because it's dealing with, all the integrals for the first part for center of mass and then also for moment of inertia. And I know that was, a struggle for some of us, but it's just a matter of practice, right? So I would definitely, I believe in the packet, there's definitely some examples where they go over these integrals. But the good news is that looking at the other FRQs, this is the only one that is a challenge to set up. But once you know how to do it, it's not too bad. The other ones we're going to see are actually very straightforward. So let's go to the second FRQ. Let's see here. So the second FRQ here, we have a small cart of mass m that can move about a curved track, and the curved track is shaped in such a way that the horizontal component of the net force exerted on the cart is proportional to the cart's horizontal displacement from the lowest point of the track. And it's located in a horizontal position, x equals 0. At time t equals 0, cart's released from x equals negative x naught and allowed to move back and forth. So this is kind of neat. This is basically, it's like a pendulum problem without it actually being a pendulum, right? So Here we have this track, and this cart's going to be oscillating back and forth, just like for the simple pendulum. And the restoring force is going to be the component of gravity that is parallel to the plane. And we have a curved plane. So when you think about this as like a little pendulum bob that's just going to be going back and forth. So here we have these little dot diagrams. And what we need to do is we got to consider the cart's motion during time interval t/2 to t. So the cart returns to its release point at times t. Oh, I gotta, hold on. How do I edit this? Wait, why won't it let me? What the heck? Oh, right. Okay. So here, all right, we need to add arrows, indicate the cart's horizontal velocity at Vx at each of the location that follows. And at Vx 0, right, Vx equals 0 above the corresponding dot. If Vx is non-zero, right, max Vf, where Vx is max. And then you're going to do the same thing for acceleration. All right, so let's think about what's going on here. So we're going to be writing down the, we're going to be drawing arrows that represent the velocity and the acceleration, but it's for the time interval. What? Okay, but it's for the time interval t/2. Yeah, t/2 to t. And the total period, t, that's the amount of time it takes to return to its initial position. So basically, this cart's going to go all the way over here to x0, and then now we're going to be looking at the motion from here to here, all right? So at position x equals x0, right, once it reaches position x equals x0, the velocity is going to be 0, all right? And it says here that we have to label that. We have to indicate that the velocity is 0 above the corresponding dot. So Vx is 0 over here, and Vx is 0 over here. Now, in terms of the direction of the arrow, make sure you don't mess this up. This is during the second half of the motion, right? So the cart's going to first move to the right, and it's going to reach position x0. Then during the second half of the motion, it's going to go from x0 to negative x0. All right, so the velocity is actually going to be going to the left. So as it starts moving to the left, it has this leftward velocity. I'm going to draw a larger arrow at the when it's at the equilibrium position. I don't think they did that in the scoring guidelines, but you know, we know this is V max, right? So this here we have to label the maximum velocity, max Vx. So let's label this as max Vx. Right, and this is just like the pendulum, right? So with a simple pendulum, we know that the velocity is maximum when it passes through the equilibrium point, and then as it passes through the equilibrium point, the restoring force is going to be going against the velocity, and it's going to bring it back to equilibrium, right? So until it reaches max amplitude on the other side. And we're going to do the same thing for the acceleration, except the acceleration is going to be 0 at the equilibrium point. And then I have maximum acceleration at the ends here. So I have maximum acceleration. And then the direction of acceleration is going to be towards the equilibrium, right? So here is my component of gravity that is parallel to the plane. And that is basically it. So that's the answer for this one. It's just like the pendulum. So here, we just did that for the acceleration. Derive an expression for the maximum speed of the cart in terms of b, m, x0, and physical constants appropriate. And the height of the track can be approximated by the equation y equals bx squared, where b is a positive constant. So again, this one's actually not too bad. It's just a conservation of energy problem. So I'll write it out over here. So this is for part B. So I know that the initial potential energy here at this position, we're trying to figure out what the velocity is at the very bottom. So the maximum speed of the cart, right? So that's going to be the velocity at the very bottom over here. So when it's down here, this is when, I'm going to consider this the height to be 0, when it's at the very bottom. So all the potential energy is going to go into kinetic energy, right? So all the object's energy is going to be in kinetic energy, just like for the pendulum. And we know our expression for potential energy and for kinetic energy. We have mgh is equal to 1/2 mv squared. But the height is represented by a function, right? So the height is a function y equals bx, right? So when x equals 0, the height is 0, and it's basically proportional to x squared. So it's a parabola, right? So this is a parabolic ramp. So for h, I'm going to write bx squared, right? So I'm going to have mg times bx squared is equal to 1/2 mv squared. I can cancel out one of the m's, right? So the m's go away, and we're writing an expression for the velocity. So here I will just multiply both sides by 2. So v squared is equal to 2gbx squared, right? And then what I have to do is just take the square root. So v is equal to the square root of, so x squared is just x. I gotta write it in terms of x naught. Okay, so we're gonna use x naught. So I have x naught here times 2gb. All right, so I'm gonna write that a little bit more cleanly over here. So the maximum velocity, b max, is equal to x naught times the square root of 2gb. And that's our answer, right? It's just conservation of energy. And on the axis below, we have to sketch a graph of the card's position as a function of time. And then we have to graph the card's kinetic energy as a function of time for the time interval. Okay, so here, let's see here. We have here the position as a function of time, and we have here the kinetic energy as a function of time. Well, this is just like for the simple pendulum, right? So I know that my position, I'm going to start off at negative x naught. I'm going to reach some maximum position x naught. And it's going to pass the equilibrium point at 1/4 t, and it's then going to reach x naught halfway through its motion, go through equilibrium again, and then go back to x naught. And it's going to look like a cosine wave. Sine wave, cosine wave, same difference. It's just phase shifted. All right, so the way this is configured, all right, it starts off at amplitude negative x naught, and then it reaches positive x naught, and then goes back to negative x naught. Now for the kinetic energy, right, so you have to think the velocity is just the slope of this graph, right? So the velocity starts at 0, then it reaches a maximum value at equilibrium, then it goes back to 0, reaches a negative value, but the kinetic energy is squared, right? So here I can just sketch the velocity time graph. Let's see here. So kinetic energy is 1/2 mv squared. For the velocity time graph, I'm going to start off at 0. Oh, whoops. No, what happened? What the heck? Wait, what? It just shifted this up. All right, well, you saw what it was originally. I'm not going to redraw that. So did it shift up everything else too? No. All right, that's goofy. Wait, hold on a second. I think it's because I held it. Oh, there we go. Let me just bring it back. It was right about there. All right, close enough. Okay, so anyways, we know the velocity starts at 0, reaches a maximum value, and then it's going to go back to 0 at 1/2 the period, right? So it's going to reach max value, go to 0, and and then reach max value at 3/4 the period, and then go like this. All right, so this is the graph for the velocity time graph, but the kinetic energy has to be positive, right? So kinetic energy is 1/2 mv squared. Okay, so it has to be positive throughout the entire range, right? So we know that it reaches a maximum value at 1/4 the period, okay? And it is going to be equal to 0 when it's at x equals x naught, okay? So it technically isn't a sine curve. It's like a sine squared. So I want to kind of give it a little bit more. Let me increase. It's going to look more like this. All right. Well, I'm not drawing it great, but anyways. So here, what's important is that it's positive, right? So the kinetic energy, it starts off at 0. It reaches max kinetic energy when the cart's at the bottom, right? So when the cart reaches the bottom, it's maximum kinetic energy. Kinetic energy goes back to 0, and then it increases again, and then goes back to 0. And that's what the graph represents. So that's what's important, is that the kinetic energy is positive, all right? And it reaches its maximum value at these two positions in time. And then for part D, if the cart were to be released at x equals -2x naught, indicate what the ratio of the cart's maximum speed to the speed you derived in part B would be. Justify your answer. Okay, so for this one, you want to be careful. So if it's at position -2x naught, that means that the height is actually going to be 4 times as high. So remember that the equation, this is like a parabolic track. So the equation for the track is bx squared, right? Let me go back here. Yeah, so we have bx squared. Okay, so my new position is -2x naught, right? So originally I was at b times -x naught squared. That's just bx naught squared. Okay, now my new position is b times -2x naught squared. So I'm going to end up with 4bx naught squared. So basically it's 4 times the height. So it's at 4 times the height. It has 4 times the energy, right? So it has 4 times the potential energy. We know potential energy is mgh. So if it has 4 times the potential energy, then it's going to have 4 times the kinetic energy. And if it has 4 times the kinetic energy, right? So we know that kinetic energy is 1/2 mv squared. Well, then the new velocity, v2, right? We know that the kinetic energy is going to be 4 times as much. So the velocity should be twice the original velocity, right? And that's basically the justification. So that's the ratio of the cart's maximum speed to the speed that was derived in part B. It's going to be twice the velocity because it has 4 times the energy, because it has 4 times the height, because that's the equation for the height on this parabolic track. And that's the line of reasoning. So I don't think that one's too bad. It's, just conservation of energy, just making sure you know how to apply it. And then let's go to FRQ number 3. So this one's an experiment. So here we have another pendulum, right? So we have to describe an experimental procedure. This time we're using springs. So we have springs of known spring constant. We need to determine the rock's mass by making a linear graph, include the steps necessary to reduce experimental uncertainty. So we're in a weightless environment, and we have to measure the mass of a rock sample that came from a planet's surface. And the scientist has a collection of springs of different masses, known spring constants, and the rock can be attached to each of the springs using a fastener of negligible mass. So how we determine the mass of the spring? Well, we're going to use the equation for the period of the mass of a spring. All right, so I'll just write out the equation now. So we have here, I'm just going to write it out. So this is the period of mass on a spring. So we have square root of m over k. All right. 2 pi times square root of m over k. So the procedure we can do is you can attach the mass to the spring and then measure the amount of time for 10 oscillations. And then you're going to divide by 10 to get the period. And then you're going to repeat the experiment for the other springs. It's kind of like what we did in the lab for the physical pendulum, right? You're going to measure multiple oscillations. 10 is a nice number that's used for these kind of experiments because it's just easy to work with. The whole idea of doing multiple oscillations or measuring multiple oscillations is that you reduce experimental error, right? So if you have some error, say 200 milliseconds, well, if you measure 10 oscillations and divide by 10, that also reduces your error by a factor of 10. So it's a neat little trick. And yeah, that's pretty much it. That's the basic procedure for that experiment. Oh, and then you want to include like how are we going to measure the period using a stopwatch? You're going to do multiple measurements to reduce experimental uncertainty, and then you're going to do it for the different springs, right? So just follow what's mentioned in the scoring guideline. So here for the data collected in the procedure in part A, describe how the scientists would create a linear graph and how that graph would be analyzed to determine the rock's mass. So just like with all the lab-based questions, we need to linearize our equation, right? So we have the equation for the period of the mass on the spring, and we know that t is our dependent variable, right? So the period of the mass on the spring depends on the spring constant, right? So our spring constant is the independent, right? So as we change the springs and measure the period with the different springs, the spring constant is the thing that we're changing as experimentalists. The period is what we're measuring. So we got to rearrange this equation to figure out how we're going to create a linear graph. So what you're going to want to do is, let's see here. Let's square both sides. So we have t squared equals 4 pi squared times m over k. All right. And we can treat, so k is our independent. So I'm going to write this as, here, let me do the little trick here. So t squared equals 4 pi squared m times 1 over k. Okay, so then if we write out the equation of a line, okay, so our t squared is going to be on the vertical axis, our 1 over k is going to be on the horizontal axis, and our slope would be equal to 4 pi squared times the mass of the rock. And that's pretty much it. So that's the data that'd be collected, and that's how you create a linear graph. I would create a graph of t squared versus 1 over k being the spring constant, and then the slope would equal 4 pi squared times the mass of the rock. And then the mass of the rock would be, right, so the mass of the rock would be equal to the slope divided by 4 pi squared. All right, and then here, now we're on the surface of the planet, and we got to determine the gravitational acceleration. And he grabs a small rock, attaches it to a string to make a simple pendulum, measures 10 small angle oscillations, and repeats for each length of the string. So he cuts the string shorter and shorter to get a nice large range of data. And here are his measurements. And what you need to do, you need to indicate what quantities could be graphed to yield a straight line that'd be used to calculate the experimental value for the gravity of the planet. So it's very similar to what we just did, except now we're dealing with the period of a pendulum. So for a simple pendulum, we know that t is equal to 1 over 2 pi times the square root of L over G, right? So L over G. And what you're going to want to graph is, let's see here. All right, so same process. So t squared is equal to what did I just do? Hold on a second. My mistake. I'm like, it's 2 pi. Okay. Yeah. Anyways. So we have 2 pi times square root of L over G. So T squared is equal to 4 pi squared times the square root. Oh, what? All right. I'm not thinking straight. Okay. So we squared both sides just like we did for the mass on a spring. And now our independent is going to be the length, and our dependent is going to be the period of a single oscillation, right? So you'd want to do just a period of a single oscillation, right? That's basically T10 over 10, okay? And then you also have, well, you're going to want to do T squared, which is T10 over 10 squared. And then you're going to use the length of the string. It's a very similar setup to what we just did, right? So we're trying to figure out what G is, and we know that L is our independent variable, right? So I'm going to write this like T squared is equal to 4 pi squared over G times L, okay? And then writing it as the equation of a line, our vertical axis should be T squared. Our horizontal axis should be the length of the string. And then the slope is going to be 4 pi squared over G. And then that's how we're going to figure out what G is. So that's the horizontal axis is going to be T squared, or at least I should say, because they want it to be all in the variables they give. So I'm going to just put T10 over 10 squared. And on the vertical axis, I'm going to put, oh my goodness, I cannot think straight right now. All right. T squared depends on L. The dependent variable goes on the vertical. Okay. So that's T squared, or in other words, that's T10 over 10 squared. Okay. And then the length is on the horizontal axis, because that's the independent variable. All right, so also if you want to put the units, this is going to be meters, this is going to be seconds squared. All right, we're recording. All right, so on the grid, all right, I'm not going to graph that. That's in the scoring guideline. I can show you an example graph. Okay, so in this one, they did T10 over 10, and they did square root of L. Same difference, functionally. It's just you're going to get different values. So if you have this kind of question, you're going to need to actually calculate the values. These questions, that's why they take so long. The lab-based questions is because you're actually performing the calculations. You're actually measuring the slope of the line. As I mentioned many times before, it's important when you graph the data, you don't use the data points to figure out the slope of the line at best fit. You have to pick 2 points on the physical line to determine what the slope is experimentally. So you apply your graph, you get the slope, and then in that case, the slope is going to be equal to what we just mentioned, 4 pi squared over G, right? So the slope is 4 pi squared over G. So then G would be equal to 4 pi squared divided by the slope. And then that's how you get the experimental value for G. And then notice that there's a large range of possible values, right? Because like depending on how you set it up and how the graph works out, these are just, possible values. But as long as you do it in a way that makes sense and, you actually measure what the slope is, you should get the approximately correct value for the gravity of the planet. All right, so almost done. One more. We have FRQ number 4. So here, this one's also not that bad. Honestly, I think other than the first one, these are pretty straightforward. So we have 3 springs. They have different spring constants, K1, K2, K3, and they're connected in series and hung vertically. Cylinder mass M hangs from the springs, and they're allowed to oscillate up and down. In this configuration, the cylinder oscillates with frequency F123. So if it's hung only from spring 2 and allowed to oscillate, it would oscillate with a frequency F2. So indicate whether F123 is greater than, less than, or equal to F2. Justify your answer without referencing or manipulating equations. Okay. Well, I'm going to at least write down an equation so that, I'm not going to write it out in terms of words. That's what you'd want to do on the actual response, but you just, I'll just explain. So here we know that if you have 3 springs and they're connected in series, okay, right, so this is spring 1, spring 2, spring 3, okay, well, springs that are connected in series, you have to use this formula. So 1 over the equivalent spring constant is going to be equal to 1 over K1 plus 1 over K2 plus 1 over K3. All right, so that's when they're connected in series. And then when they're connected in parallel, right, then it's just the sum of the spring constants, K1 plus K2 plus K3, ... Okay, it just keeps going. So we're going to be seeing this kind of equation again when we deal with capacitors and resistors. They follow the same kind of functional form. But yeah, for springs in series, the equivalent resistance is going to be less than that. I can't. Not equivalent resistance. That's for resistors. The equivalent spring constant is going to be less than that of the individual springs. And if you think about it, it kind of makes sense, right? So let's, I think when we first learned this, I gave an example of 2 force meters, right? So if I have 2 force meters hanging back to back, and they're measuring like the tension in the string, well, that force meter is going to displace a certain amount for a given force, right? So say it displaces, 10 centimeters for 10 newtons of force, right? So it's 100 newtons per meter. Well, if I hook up another spring constant immediately after it, it's also going to register 10 newtons of force, but then the total length of the, of the contraption would be twice as large, right? So the effective spring constant of that system is half as much, right? It would, stretch 20 centimeters while only experiencing 100 newtons or 10 newtons of force, my bad. But anyways, this is the equation for when you have multiple springs, whether or not they're in series or they're in parallel. To draw a little picture for parallel, is when they're like this, right? So say like they're hanging off of a box. So like these 3 springs connected to a box, or they have them connected back to back. And the justification is basically, it comes from the equation, right? Don't just write the equation. You have to like spell it out. But the equivalent spring constant, okay, for the series, it has to be larger than that of the individual spring constants for the individual springs, because it's the sum of the reciprocals. So it's like the reciprocal of the equivalent spring constant is 1 over the sum of the reciprocals for the individual springs. So yeah, that's basically it. In terms of the frequency, my bad. So we know the spring constant is less, all right? But now why is the frequency less? Well, the frequency of a mass on a spring, all right, so for this equation, it's 1 over 2 pi times the square root of k over m, all right? Usually I just memorize it in terms of like angular frequency, all right, square root of k over m, but we know that angular frequency is equal to 2 pi f, so then f, the frequency, is just 1 over 2 pi times angular frequency. So that's the equation, okay? So that's the equation, and we can see that because the spring constant of the series setup is smaller, and we're dealing with the same mass, m, the same cylinder, the frequency F123, right, that has to be less than the frequency of just spring 2. So for the next part is determine the spring constants really as followed. 2K1 equals K2, which equals K3 over 3. Okay, and we have to derive an expression for the oscillation of the frequency F123 express your answer in terms of K2, M, and physical constants as appropriate. So now we're going to plug it into the equation. So now we have 1 over K EQ. And we have to write it in terms of K2. All right, so we're going to do a little bit of substitution here. So instead of K1, I'm going to write K2 over 2, right? So if 2K1 equals K2, then that means K1 is equal to 1/2 K2. And then if K3 over 3 equals K2, then K3 is equal to 3K2. All right, so now let's plug these into the formula that I wrote out. We have here 1/2 K2 plus 1 over K2 plus 1 over 3K2. And we're going to want to have common denominators, so I'll set all the denominators to 3K2. So we have, whoops, not 3. What am I doing here? That's 6. So 6 over K 3K2 plus 3 over 3K2 plus 1 over 3K2. And we end up with 10 over 3K2. But don't forget, very, very common mistake, you have to take the reciprocal. All right, so a lot of people, they get to that point when dealing with resistors or capacitors or springs, and then they just leave it there. You have to take the inverse of that. So the equivalent not the equivalent resistance, the equivalent spring constant is 3 over 10 times K2. And that's the answer. Well, no, it's not. It's the frequency. All right, I'm almost done. So the frequency F123 is equal to 1 over 2 pi times the square root of K over M, but we're going to write it in terms of K2. So 3K2 over 10M. And that's what the answer is. All right, and then the cylinder of 2M were hung vertically from spring 2 and only allowed to oscillate. Indicate where the oscillation frequency would be greater than, less than, or the same as the frequency you derived in part B. All right, so now here we know that the F of 2, so now we're going to hang a mass 2M from it. So now we have this equation, 1 over 2 pi times the square root of K2 divided by 2M. All right, and basically you're comparing this expression with the expression from part B. And if you look at it, right, so just to simplify, I'm going to set this equal to 1 over 2 pi. Or we're going to compare it, right? So I'm not going to set it equal to. We're going to compare these two expressions. So I have 3 over the square, 1 over 2 pi times square root of 3 over 3K2 over 10M. And here we have K2 over 2M within the square root. But we know that K2 over 2M, that's greater than 3K2 over 10M, right? Because, well, 1/2 is greater than 3 over 10. Okay, so that means that it has to be greater than. Justify your answer. Well, that's the justification, right? So you have these two expressions, all right? You know, well, even though I'm hanging a cylinder with twice the mass from only spring 2, because the equivalent spring constant is 3/10 of spring 2, looking at the equation for the frequency of the spring, even though it's twice the mass, it's still going to be larger than the combination, the series combination of the 3 springs. And yeah, that's basically it. So again, this problem wasn't too bad as long as you know this, right? So make sure you know this in general. This has come up more than a couple of times, right? Dealing with springs in parallel or in series. So, you know, make sure you're aware of that. And then the rest of it's just, you know, using the equations to justify your answers. So anyways, if you have any questions, just let me know. I'll be available after school tomorrow as well if people want additional help. And then always feel free to send me an email over the weekend. But the plan is to take the test when we get back. And then we'll be all finished with mechanics, and we can finally move on to E&M. Well, anyways, let me know if you all have any questions.